You are listening to The Vocal Technologist. Spoken tech for your ears.
Tools are getting better, output is getting worse. Both are true.
Yeah, it is a contradiction that is becoming pretty impossible to ignore in engineering right now.
If you are listening to Vocal Technologist, you know we like to get into the guts of how things actually work. And right now, we are taking a proper look at a stack of engineering postmortems and research papers just to untangle a really strange reality in the tech world.
Right, because things are breaking in unexpected ways.
Exactly. We need to suss out why our benchmark tests are lying to us, why giving AI better tools is actually slowing developers down, and, how engineering teams at places like Netflix, Grab, affirm how they're ripping out these bloated architectures to build systems that finally move fast.
When you look closely at these internal reports, what we're really tracking is a massive shift away from brute force computing.
Like just throwing more servers at a problem.
Right, or throwing more data at it.
Yeah.
Now, we are shifting toward precision engineering. The underlying architecture and the rules governing it, well, they matter significantly more than raw scale now.
Right, so we should probably start by looking at the yardsticks we use to measure success because, frankly, they are currently completely broken.
They are entirely flawed. Take AI text-to-SQL benchmarks, for example.
Those are the standardized tests we use to grade how well an AI model can translate plain English into database queries, right?
Exactly. The industry relies heavily on these benchmark tests called BIRD and SPIDER to rank the models. But researchers have found that the gold standard queries, like the answer keys used to grade the tests, they actually contain incorrect answers.
Wait, so we are training AI to be confidently wrong because the answer key is basically having a lend of us.
Yeah, that is essentially what is happening. The way execution accuracy is measured right now, it can actually reward an AI model for reproducing the benchmark's mistakes.
That is wild.
And it penalizes it for providing the correct answer. The evaluation systems are just checking if the output strings match, or if the code executes without a syntax error. They completely ignore crucial data semantics.
When you say data semantics, you mean the actual logic of the business, right? Like an AI might write a query that adds up the sales column and returns a number.
Yes, exactly.
But if that table includes daily snapshot records, it is just double counting everything. So it executes perfectly, but the number is a complete fabrication.
That is 100% spot on. Semantics involves understanding join cardinality, you know, how tables relate without duplicating rows, or grain, which is the level of detail in a row, or additivity, like your sales example.
It's like a math teacher who firmly believes 2 + 2 = 5.
Right.
The smartest kid in the class ends up failing the test simply because they know the real answer, while the kid who memorizes the flawed textbook gets top marks.
That is a great way to put it. To evaluate these models properly, you really have to abandon rigid answer keys. There is a method gaining serious traction called geval.
Okay, how does that work?
Well, instead of a simple pass-fail string match, you have a language model generate its own scoring steps from a rubric via chain-of-thought reasoning.
So the AI is explaining its working out before it grades the test.
Precisely. And then, instead of just returning a single printed digit for the final score, it computes a weighted expectation over the token-level probabilities for each possible score.
Wait, why token probabilities instead of just asking for a score out of 10? Is it because a language model is just rolling the dice on the next word, so a single answer is too unstable?
Exactly that. By looking at the underlying probability distribution of the tokens the model considered, essentially asking the model how confident it is across multiple possible scores, the evaluation becomes much more reliable.
Ah, I get it.
But there are two hard rules for this to work. First, you must use a judge model from a completely different family than the one you were evaluating to prevent bias.
So you can't just have one company's model marking its own homework.
Right. And second, you have to calibrate the rubrics against human-labeled examples.
That makes a lot of sense. But, I mean, it is not just AI getting graded poorly. Human metrics are failing, too. If you are listening to this and you manage a data team, you probably know exactly what dashboard sprawl feels like.
Oh, absolutely. Dashboard sprawl is creating three major costs for data organizations right now. First, it destroys trust. Second, it wastes incredible amounts of warehouse compute.
And the third.
It leaves you with dead artifacts everywhere. One organization documented hundreds of dashboards, but only dozens were even opened in a given quarter, Roughly 90% were completely unused.
That is heaps of wasted cash. Just servers spinning up every night, crunching numbers to refresh charts that literally no human being is looking at.
It is. The mitigation here is a practical framework called the 90-90 rule.
Okay, I like rules. What is it?
If a dashboard has no views for 90 days, you automatically archive it. If another 90 days go by and no one complains or asks for a bag, you delete it entirely. It just forces hygiene into the system.
Which brings us to the part nobody's really saying out loud. If our dashboards are ignored and our AI benchmarks are dodgy, what are these highly paid data teams actually doing all day?
Well, they are putting out fires. There is a concept called the data anarchy tax.
Yeah.
Organizations without dedicated data product owners spend 45% of their week on reactive work.
45%.
Yeah, that is almost half their time just fixing broken pipelines, tracking down missing data, answering panic questions from the business, compared to just 27% for teams with clear ownership.
I imagine introducing AI into a messy environment like that just makes it worse. Like, if you don't own the data, the AI just makes your lack of ownership faster and more destructive.
It absolutely amplifies the chaos. Teams with clear ownership, meaning someone is explicitly assigned to manage specific data sets, they actually see an 18-point sentiment gain when they introduce AI tools.
And the messy teams.
Teams without structure see a 26-point drop. The AI just exposes the broken foundations.
So how do you actually govern that? Because you can't just tell an AI to figure it out on its own.
No, you build strict frameworks. Expedia Group is a great example. They mandated that every single AI model must tie directly to a measurable business outcome. It must run on shared platform foundations rather than some bespoke stack and have defined owners.
That sounds like a lot of discipline.
It is. And you see this philosophy in open source tools too, like the analytics agent framework called Now. It is fascinating because it forces data teams to own what they call context engineering.
Context engineering. That sounds like a fancy way of saying they actually define the rules and relationships of the data before the AI gets its hands on it.
That is exactly what it is. The data team owns the data profiling, the semantics, the boundaries. Now provides a clean UI for business users, but a command line interface for the data team to build that context layer.
Right.
And then the AI is completely bounded by it. Because honestly, if you give an AI too much freedom, its performance becomes a bit ordinary. Look at what happened with GitHub Copilot.
This is one of the most instructive failures we looked at. GitHub tried to improve Copilot's code review capabilities by giving it better shared tools.
Yeah, thinking more context would mean better suggestions, but the performance actually got worse.
Why does giving an AI better tools make it worse at its job?
The token costs rose, and fewer bugs were caught. The problem was the instructions were too generic. Because the agent was told to review the code using these broad tools, it started browsing the entire repository instead of focusing on what actually changed.
Oh, I see.
It got distracted by millions of lines of irrelevant code.
It is like sending a mate to the pub for a pint and they come back with a whole keg because you didn't specify exactly what you wanted.
Yeah, that is pretty much it. The solution was incredibly specific constraints. They rewrote the instructions to say, start from the diff, narrow with grep and glob, read exact evidence with view.
So only look at the exact lines that changed, search for specific terms, and only read the specific files that matter. If you reckon picking apart these engineering failures is as fascinating as we do, hit subscribe. It genuinely helps us out.
By forcing the AI to start small and only expand when necessary, GitHub cut the average review cost by 20% with zero loss in quality.
That is massive.
It is. And that exact same philosophy, narrowing the focus to the exact source of a change, that is driving how we build data pipelines now too. It is the core of the updated Shift Left manifesto.
The lesson from Copilot is that context is everything. And data engineers are having that same realization. Historically, data lineage like tracking where data came from and what happened to it, that was handled downstream in the data warehouse.
Right.
Why on earth did we ever accept trying to figure out what data means after it has already been processed?
Because we didn't have the tools to do it earlier.
Yeah.
But it is entirely backward. The warehouse only captures data after its meaning has been defined by the upstream application.
Right, it's too late.
The updated manifesto argues that lineage must begin in producer code. When a software engineer writes a pull request to change a feature, the data lineage is captured right there in the code.
So you see exactly what downstream dashboards will break before you merge the code.
Exactly. It exposes ownership, the blast radius of a change, and sensitive data flows directly in the pull requests. And orchestration tools are building AI guardrails directly into this foundational layer to enforce it.
Like Apache Airflow, right?
Yeah. Airflow is using semantic schema validation to catch data drift instantly.
How does that actually work in practice? Like on a Tuesday morning, what does that look like?
Well, instead of a pipeline failing silently because a column changed from an integer to a string, the AI validates the semantic shape of the data against expected schemas before the job even executes.
Oh, wow.
They also use persistent state to reconnect failed jobs, and they use language models to classify pipeline failures.
So the AI decides whether the system should retry, delay, or escalate the alert to a human.
Exactly. It reduces the firefighting tax significantly.
Shifting everything to the left like this, it has to fundamentally change privacy, too. You can't just slap a redaction filter on a column at the end of the pipeline anymore.
Privacy engineering goes far beyond redaction now. It requires continuous classification, purpose-based access, and fit-for-use controls built right into the platform. A good example is deterministic tokenization.
Which is where you replace sensitive data, like an email address, with a consistent token. So internal teams can still join tables together without seeing the real data.
Right. It supports internal joins beautifully, but you have to remember, it remains pseudonymous, not anonymous.
Because if a recipient gets those tokens, they might still link records back to an individual based on behavioral patterns.
Exactly. True privacy engineering requires auditable policy enforcement at the earliest point of data creation.
When you fix that foundation and you shift governance to the left, the architectural speed improvements you get are frankly absurd. We should talk about what a firm did.
That is a brilliant case study.
They had a pre-checkout messaging service built as a massive Python monolith, and they completely rebuilt it into a Kotlin microservice powered by a rule engine.
The performance gains were substantial. They cut P99 latency by 50%. But the real win was developer velocity. Because it runs on a rule engine now, adding a new pricing experiment just means writing a new rule against existing attributes.
So instead of engineering an entirely new code path and waiting for a full deployment cycle, they just update the logic rules. That reduced their experiment setup time from 2 months down to just 4 days.
It is incredible.
2 months down to 4 days. That is not a software update. That fundamentally changes how a company operates. You can test 15 ideas in the time it used to take to test one.
We are seeing these massive efficiency leaps across the industry when companies re-architect for reality. Razorpay had a huge problem with their data warehouse refresh times.
Right.
They were scanning massive databases every single night just to find a few updated rows.
Yep.
It is a huge waste of compute. They solved it by replacing full table scans with incremental graph traversal and secondary indexes.
Incremental graph traversal sounds incredibly dense. How does that actually speed things up?
Think of it like a librarian managing a massive archive. Instead of reading every single book in the building to figure out which ones were added today, the librarian just checks the daily delivery log and walks straight to those specific shelves.
That makes sense.
Razorpay built a layer that deduplicates daily changes, and the graph traversal only processes the rows that actually changed, back-traversing dependencies to enrich the updates. It cut their warehouse refresh time by 90%.
That is brilliant. Grab did something similar with their data lake, moving over to Apache Iceberg. They migrated a petabyte scale setup from Hive Parquet and immediately got a 10 times query speedup and a 95% drop in S3 API costs, plus like 50% compute savings.
It is a massive shift in how we handle storage.
I've never fully understood how Iceberg achieves this. Object storage is notoriously dumb. It is just a bucket of files. How are they getting a dumb bucket to act like a high-speed database without locking it up?
It comes down to adding ACD guarantees to object storage. Frameworks like Iceberg, Hootie, and Delta Lake do this through a clever metadata log and an atomic publish step.
Okay, so a metadata log.
Basically, an ingestion job can write thousands of new files to the data lake, but the readers querying the data do not see them yet.
It is like a restaurant kitchen. The chefs can be preparing dozens of ingredients, but the waitstaff doesn't take the plate to the customer until the head chef rings the bell.
That is exactly it. Readers get snapshot isolation. They only see the data after a single atomic metadata operation publishes the commit, so you never read half-written data.
That solves so many concurrency issues.
It does. Furthermore, the tooling around this is maturing. There's a new API design called Lakekeeper's Generic Table API, It allows entirely different data formats, like Lance datasets used in AI, to be governed by the Iceberg catalog.
So you get all the access controls and lifecycle rules without having to convert your AI data into Iceberg format.
Exactly. With frameworks like that, companies are handling unimaginable scale.
Hmm.
But here is the twist. They are starting to figure out that just distributing the workload across 100 servers isn't always the best answer.
Scale is forcing a lot of reevaluation. Take Arcesium. They migrated a 170 terabyte, 15 trillion record profit and loss warehouse from a traditional relational database to Apache Iceberg using DuckDB.
Using DuckDB to process 15 trillion records is serious business.
It really is, especially since DuckDB is famous for just running locally on laptops.
They paired it with a homegrown execution layer called Swift Lake and Kia for autoscaling. They cut ingestion runtime by 80% and dropped their infrastructure spend by 40%.
Huge.
And Netflix has a similar story of wrangling extreme scale with their service topology. They built a sub-second queryable dependency graph.
To map out how all their microservices depend on each other?
Right.
But the load variance they deal with has to be insane.
It is. The hardest problem Netflix faced was a 100 times load variance caused by power law traffic. When a new show goes viral, traffic concentrates massively on specific services.
How do you track that without the tracking system itself crashing?
To prevent that data pipeline from collapsing under the weight of hotspots, they used eBPF flow logs, which are incredibly fast and low overhead, and multi-stage redistribution.
Multi-stage redistribution. So if one server is getting hammered by viral traffic, what does the system actually do?
Think of it like opening emergency spillways on a dam when a storm hits. Instead of letting one aggregation server drown under a viral show's traffic, the load is instantly fractured, hashed, and routed to a wider pools of reserve nodes to distribute the pressure evenly.
When you operate at that scale, you have to build serious defense mechanisms. Even basic things like cache layers can fail spectacularly.
Cache layers are essential, but if a popular key expires, you get a cache stampede. Every request suddenly hits the backend database at once, taking it offline. Engineers use defenses like TTL jitter to prevent this.
TTL jitter being time to live jitter. So instead of 10,000 users having their cache expire at exactly midday, causing a massive spike, you add random variance, a few seconds here or there, so the requests trickle into the database instead of flooding it.
Precisely. And within the database itself, there are clever optimization tricks. PostgreSQL, for instance, can perform partition pruning on columns that aren't even the partition key, provided you add cheat constraints for predictable ranges.
Which means
It makes the database optimizer incredibly smart. It knows it can completely skip irrelevant local index scans, avoiding massive disk I/O.
knowing how a single machine or database works at this deep level is becoming more important than ever. Which brings us to the benchmarking shocker with polars. This completely challenges the big data mindset we have had for a decade.
It is a massive upset. Researchers ran a 1 terabyte TPCH benchmark test. They compared a distributed polars cluster running on 32 separate nodes against a single massive Amazon instance, an M8i.32x large, to be specific.
So 32 machines networked together versus one giant machine.
Both setups had the exact same aggregate hardware specifications. And the 32-node distributed cluster only won on I/O-bound queries, and only because its burst network bandwidth was higher, 400 gigabits per second burst versus 50 gigabits sustained.
Okay, but what about the complex stuff?
On join-heavy queries, the single node completely destroyed the distributed cluster.
It is like having 32 chefs in a massive kitchen. It is great if you need to chop 10,000 onions independently, but if they have to constantly hand ingredients back and forth to make a single complex soup, the communication overhead slows everything down. One really fast chef working alone on one bench is just way better.
That is exactly what happens. On joins, the network shuffle overhead across the cluster entirely erased the games from parallelisation. And by the way, if you're looking to build your own skills on these concepts, there is a free platform called Ship That Code where you can build databases from scratch. Also check out Awesome DuckDB for a curated directory of tools.
Because engineering is getting this precise and hardware is getting this powerful, it feels like the era of a million disjointed data tools is finally ending. The market is consolidating rapidly around these highly efficient architectures.
We are seeing a wave of strategic acquisitions proving this. Prefect is acquiring Dagster.
Oh, wow.
Yeah, they are retaining the names and pricing, but pairing Dagster's outcome tracking with Prefect's execution engine. Cloudflare just acquired Arroyo, a Rust-based SQL stream processor.
To add stateful joins directly into their edge pipelines.
Exactly. Early experiments even show Cloudflare's R2 storage combined with Iceberg functioning as a lightweight lakehouse.
Are we finally moving out of the move fast and break things era and into an era where we actually care about the plumbing? Because it seems like security and efficiency are taking over everything.
We absolutely are. Free tools like Graysite for Snowflake cost observability show that efficiency is top of mind. And look at ClickHouse. They are now shipping hardened Docker images built on a minimal base. They stripped out the shell, the package manager, and all the network tools entirely.
So if a hacker somehow gets in, they literally have no tools to use, no bash, no curl, nothing.
Exactly. This dropped their common vulnerabilities from 8 medium-severity CVEs down to absolute 0, while keeping database behavior identical. The focus across the industry has shifted completely to efficiency, security, and strict governance.
So we have picked apart broken AI benchmarks, watched data governance shift back to the source code, and seen single nodes beat massive distributed clusters. It leads to a pretty profound realization.
We spent the last decade obsessed with big data and infinitely scaling distributed clusters, thinking everything had to be a massive network of machines.
Right.
But with hardware getting so incredibly powerful, the future of data engineering might actually just be massively hyper-optimized single machines.
It makes you wonder how much of our current infrastructure is just complexity for the sake of complexity. We will leave you to think about that one. Vocal Technologists, see you soon.
Spoken Tech, for your ears.